Hey guys! In this video we're going to be talking a little bit about states of matter and what happens when chemicals change from one state of matter to another. So, first thing we're going to talk about is something called kinetic molecular theory. So this is a theory that says matter is made of tiny particles, so things like atoms and molecules, that are in constant, random, straight line motion. So everything's moving around really quickly in a random direction, but not in curves, just in straight lines. That's the easiest way to model how atoms and molecules move. Now, kinetic molecular theory also tells us that as we increase the temperature of a sample, the particles are going to move faster. So at higher temperatures, the velocity or the speed of the particles will be higher, which should make sense to you. When you heat things up, they move faster. And some of this will come into play when we talk about these different states of matter. So we're going to answer some of these questions about solids, liquids, and gases. So solids, do they take the shape of their container? Well, I can even show you this. Here's a beaker. Here's a glue stick. Put the glue stick in the beaker. The glue stick is not taking the shape of the beaker. So that answer is no for solids. Now liquids, they do take the shape of their container. If I pour some water into this beaker, the water will kind of like fill up the bottom of the beaker. So it's going to take the shape of the beaker. So yes, and then gases also will take the shape of their container. Okay, solids, do they fill up the volume of the container? So again, the glue stick is not filling up the whole volume of the beaker. So that answer is no. If I put water in here, it would take the shape of the beaker, but would it fill up the whole beaker? No, unless I put in exactly enough water in to fill up the beaker. So liquids are a no. But gases will. They will move around until they fill up the entire beaker. So if I put some gas in here and close this off, it will fill up the entire beaker. Okay, so let's talk about how much kinetic energy these different states of matter have. So solids, you can imagine the molecules they're moving, but they're not moving very much. They're kind of stuck in place. So they have low kinetic energy or low motion. Kinetic energy is kind of equivalent to motion. It is energy of motion. Liquids have more kinetic energy than solids, so we're going to say medium. And gases are moving around so quickly they have tons of kinetic energy. So very high kinetic energy for gases. The attractions between the molecules. In solids, they're going to be very attracted to each other. That's why their kinetic energy is low. They're going to have really high intermolecular forces, which we talked about last chapter. Or they're going to be like ionic compounds that are really attracted to each other. So very high. Again, in liquids, it's in the middle. So they're attracted to each other enough that they kind of flow together. But they can move a lot more than solids. And then gases are not very attracted to each other. And compressibility. So can you compress these into smaller shapes? So this glue stick, not compressible. So very low compressibility. Liquids, also not very compressible. It's really hard to compress water. But gases are very compressible. So that's going to be high. Okay. So there are these graphs that you need to know how to read that kind of show what happens as a substance changes from a solid to a liquid to a gas. These are called heating curves. So if you look at this graph, you'll notice the x-axis is time. So as time goes on and we're adding heat to this substance, so let's say we've got like a beaker of ice and we've got it on a hot plate, so we're heating it up. So as time goes on, the temperature of the ice is going to increase because we are heating it up, okay? So at different points on the graph, we're going to have different states of matter. So this section between A and B, the ice is going to be solid, or whatever substance we're heating up. This is where it's a solid. And you'll notice the temperature is increasing as we're heating up the solid. Now, it's going to get to its melting point, and until all of the ice is melted, it's going to be at the exact same temperature. So these flat line parts, these are called phase changes. This is where we're changing from a solid to a liquid, or a liquid to a gas. So this one is melting. And then once all of the ice has melted, it's going to be a liquid. So from C to D, it's going to be a liquid. Imagine again that we have like a beaker of ice, or a beaker of water now. We're heating it up. And at some point, it's going to get to its boiling point. Now, you should know from your life experience, when you put a pot of water on the stove and get it to its boiling point, it doesn't increase in temperature once you get it there, right? It stays at the same temperature until it all boils off. So this is the boiling point. And what's going on with this graph is that the energy in these sections that are going up, the energy is going to raising the temperature of the substance. But when it's changing phase, all of the energy is being used to change that solid into a liquid. So the temperature isn't increasing. Energy is still going in, but the energy is going into turning the ice to water, or turning the water into water vapor. Okay, and then if we contained all the water vapor and kept heating it up, we could get the gas to heat up as well. Okay, so you just need to understand what these graphs are and how to answer questions about them. So I want to show you a couple other kind of versions of this graph. I'm going to zoom in because this one's a little bit small, hard to see here. So this one looks very similar to this one up here, but instead of time on the x-axis, it's got energy. So I could ask you questions like, how much energy does it take to melt this substance? So we look right here at the melting section, and it looks like B starts at about like 1 right here, and this is maybe, I don't know, 8. So the energy needed to melt this substance would be like 7 kilojoules. Joules are a unit of energy. The energy that is needed to boil the substance is a lot more. We go down here, this is about at 15, and this is about at maybe 55, right? So this is probably about 40 kilojoules to boil. So usually it takes more energy to boil things than to melt them. But those are the kinds of questions you can get asked about these heating curves with energy instead of time. And I also just want to let you know that there is such thing as a cooling curve. So this is like the opposite. This is like if we take a pot of boiling water outside on a freezing day, it's going to cool down and eventually it'll freeze. So here it's going to a gas, and here, instead of this being boiling, this would be condensing. That's where you have a gas turning into a liquid, right? And then this point where we're going from a liquid to a solid, this would be freezing. So the freezing point and the melting point are the same temperature, but they're just the opposite process. Same thing, condensing and boiling happen at the same temperature, just one is if we're cooling it off and the other is if we're heating it up. Hopefully that makes sense. One last thing I want to tell you about energy. So in these sections where the graph is going up, we would say we are increasing in kinetic energy. So right here, kinetic energy is increasing. And you can see energy is increasing the whole entire time, but in these sloped parts, it's the kinetic energy that is increasing. And that's true right there, that's true for that section, that's true for this little section. This flat parts, during the flat parts, potential energy is increasing. All right, so that is states of matter and heating curves and how to read them. Hopefully that makes sense. Let me know if you have any questions.